Why don't we get started? Welcome everyone to today's webinar. It's a pleasure to introduce today's speaker, Mike Armstrong from the Material Science Division at Livermore. Mike is a specialist in ultrafast techniques applied to the study of materials, from tabletop optical lasers to electron imaging to free electron laser methods. A little bit about Mike's background. He has a bachelor's degree from New Mexico State University in both musical performance and physics. From there, he moved to Rochester, where he obtained a master's and a PhD in physics. After several years working in industry, Mike was appointed as a postdoc at Livermore. That was in 2004, and he became a staff scientist there in 2007. Mike has received a number of awards, including Fellowship of the American Physical Society in Instrument Science and an Innovation Award from Microscopy Today. Mike has also been a valuable collaborator in CDAC, as well as a partner in an Energy Frontier Research Center that we managed beginning in 2009. So Mike, we're looking forward to your talk. Thank you for volunteering to give it.
Thanks very much for inviting me. So I am gonna, if it's okay with everyone, I'm gonna stop my video. I'm just worried about, bandwidth issues and just having bandwidth get in the way of the talk. So I'm gonna stop sharing my video here, but I will continue talking, and I have not vanished. Okay, so today I'm gonna talk about experiments that we did a long time ago, in 2016, actually, July of 2016. So it's been almost 6 years. They were on the graphite to diamond phase transition using ultrafast shock compression. And we did these experiments at LCLS using ultrafast pulses. But we've had a real struggle to try to understand this data. And one of the main reasons for that is because it's just in such a different regime than people are conventionally used to. So the regime that we're in is highly non-equilibrium. We are talking about very short timescales, picosecond timescales. And over those timescales, materials can reach highly non-equilibrium states prior to actually equilibrating. And so I'm going to show some examples of that. And this basically made it difficult for us to interpret our data. So for a long time, we were trying to interpret it in terms of more conventional viewpoints, but then eventually we had to look at things a little more deeply. And I hope we have a better handle on it now. So we just recently had a paper accepted to the Journal of Applied Physics. Again, after years of struggling to get something published, it was finally accepted like a week ago. And one of the other issues in getting things published was we have something like 25, 27 authors on this paper, and there were a lot of internal arguments about the right way to interpret this data, but I hope we came up with the right final conclusions. Oops. Right, so first I wanted to talk about shock waves, and just have a little bit of an introduction to shock waves for people who aren't familiar with them, and then talk a little, in addition, a little bit about ultrafast shock waves. So shock waves are one way that you can change the thermodynamic state of a material. Traditionally, you have a very strong pressure wave moving through the material. So the kind of upper right here is the canonical view, where there's a discontinuity at a shock wave front between the ambient material, starting material, and the final equilibrium material. And due to the resolution of typical measurements, usually in the past, these changes are effectively instantaneous. So you get something like a Heaviside function, the thermodynamic variables, very, very rapid change on the time scale of the resolution of the experiment generally. And they're generally assumed that that final state is in traditional experiments is assumed to be at equilibrium. And so they can be used in early shock experiments were used to calibrate diamond anvil cell measurements, actually, which are most likely at or closer to equilibrium. But on ultrafast timescales, what if you look on ultrafast timescales, the change in state is not actually instantaneous. In fact, it has some spatial extent or some temporal extent. And we looked at this, a little bit more than 10 years ago. So I have a plot on the upper right here where you can see basically the change in a surface velocity as a function of time for something like a 40 GPa shock wave in aluminum. And you can see that this change happens over something like 20 picoseconds. Now, this is in a situation where the material state is fairly simple. It's just plain plasticity. So there aren't a lot of different phenomena that are involved in the state change. But if we're looking at a more sophisticated kind of material or more sophisticated mechanisms, like for instance, a phase transition, then we might see something a little bit more complicated, like for instance, a two shock situation where there is initial shock to get to just below a phase transition pressure in a material, and then another wave associated with the actual phase transition itself to the final pressure. An example of that is this is a classic example from a paper by Nellis, where they show the phase transition actually that we're going to be looking at today, graphite to diamond. Okay, so whoops, let's see. Right, so what we are trying to look at, I think of as being more analogous to a transition state in physical chemistry. What we're trying to look at are the intermediate states between that initial equilibrium and the final equilibrium. And to do that, we have to look at very high time scale or very short time scales because the materials do change very quickly. And these are the kinds of changes in materials that largely have only been accessed with simulations. So there are a couple of examples here. One is of nucleation of a new phase, and the different colors. This is the center here. This is an illustration from Babak where they're showing a phase transition. I think this is an iron. I probably should have written it on the slide. But then they have two different phases in one nucleus, and that is the result of surface interactions. And so what governs that? How do we calibrate simulations to correctly emulate that? You really need to look on short time scales, and in the case of nucleation, short length scales to be able to characterize that. And then there's another, on the right here, there's another simulation from Von Olenik's group, where they're showing sort of nanoscopic interactions with dislocations and elastic waves emanating from plasticity. Again, this is something that's very difficult to observe directly because of the very short time and length scales. But we can get sort of an aggregate view of those kinds of processes. So there was a paper that we published in PRL in 2011 where we looked at shock transformation of aluminum, at various different final pressures. And the thing that I wanted to note here was that we can reach very, very non-equilibrium states. This is, if I didn't already say it, this is an aluminum. And then as we turn the pressure down where the shock wave is no longer overdriven, we begin to see this multiple wave structure here. And this multiple wave structure is basically an elastic plastic transition where the initial rise is mostly elastic, and then over time, the kinetics of plasticity have time to occur, and we see the equilibration to the final pressure. But the thing to note here is that this initial elastic-like compression is much, much stronger than what you would find in aluminum near equilibrium. So the equilibrium yield, the quasi-equilibrium yield strength of aluminum is closer to 100 megapascal, so about 100 times smaller than this elastic precursor that we measure on very short time scales. And so the point there is that we really are looking at extreme non-equilibrium state, intermediate states that can happen within shocks. So I wanted to make a quick point about scaling. So there is a nice advantage of doing experiments on short time and length scales, as these experiments are. The amount of energy that is required to do a shock compression experiment depends on the time scale of the experiment to the third power, basically the scale of the experiment to the third power. And so if you are able, if the phenomena that you're interested in looking at are short enough, so that you can look on picosecond, sub-nanosecond timescales, and that potentially can save you a lot of energy. So if you go from an experiment that requires a 10 nanosecond drive to an experiment that requires, say, a 1 nanosecond drive, you'll save a factor of 1,000 in energy, which is very nice for a couple of reasons. One, because the lasers can be much less burdensome to use. But then also something that doesn't come up much is that there is a change in rep rate for lasers between about the 100 joule to kilojoule level to the sub 100 joule levels. So if you're operating with a hundreds of joule laser, then your typical rep rates are going to require something like, maybe an hour of cool down between shots. But if you can get into the tens of joule range, then you can take a shot, potentially very fast, on the order of perhaps a minute to tens of seconds. And then another point related to this is that the amount of throughput that you get specifically from an X-ray experiment also has a very favorable scaling with scale of the experiment. And so if you were able to make the experiment, say, 10 times smaller, then the throughput, assuming an average power in your drive, where you're adjusting the rep rate of the drive consistent with that average power, then if you can make the experiment 10 times shorter in duration, then you can get potentially 100 times better throughput. So it can be very useful, particularly for situations where you have complex phenomena like in this experiment. And so when we originally did this experiment years ago, we wanted to take advantage of that. So we made samples with lots and lots of potential shots on this. So these samples are engineered with silicon. We have a metal layer on top of a silicon nitride layer on silicon. And then we use silicon, synthesis methods, silicon methods to burn out or chemically etch out a well up to the silicon nitride level, and that leaves us with a film of an ablator and the sample. And we can do that, and create many shots on a single wafer. And so here's an example where we have something like 15 by 15 array on something like 1.5 by 1.5 silicon array. And you can see these are many of the shots that we took when we did this experiment. When we did the experiment, we did a combination of zirconium and HopG at the same time. And I'm going to talk about the zirconium first, just to give a little bit of perspective on just a little bit of, just to ease into the HopG work a little bit more. We learned an awful lot, even working with zirconium, which should be much closer to equilibrium than HopG. So I wanted to talk about that first. Just some parameters about the experiment. So these are, very short time duration experiments. We have 130 femtosecond X-ray pulses that we're using to interrogate the shocks, and the drives are on the order of 120 picoseconds. So initially we looked at zirconium, and so these are the kinds of conditions we looked at. I'm not really going to talk a lot about our zirconium results. I mainly want to talk about the mechanics of shocks moving forward. We also shocked up to the melt in zirconium, and that's not really very clearly on this phase diagram. But in case you're wondering, when I talk about some of the zirconium results, we're basically talking about shocking into the omega and beta solid phases of zirconium. So this is basically the mechanics of our experiment. So we have XT diagrams from simulations at the top here at 3 different energies. So the idea is that our laser pulse comes into the sample from the left, the ablator. Here, I probably should have put a vertical line in these plots. So where we see this shock reflection here, to the left of that is our aluminum ablator. To the right is our sample, which in this case is zirconium in the simulation. And so we have this roughly 1 to 200 duration, picosecond duration pulse that comes in at the ablation plane to the aluminum, and then that launches a shock wave into the aluminum, which then is reflected somewhat at the zirconium, and then because of the impedance matching between zirconium and aluminum, a 30% or so higher shock pressure is launched into the zirconium, and then that propagates through. But this is pretty different than what you would see in a longer duration experiment. Typically, what you would see in an experiment where people are more interested in equilibrium states is a longer duration pulse coming in initially. So you'd see pressure at this input plane for a much longer duration of time. And then you would see basically more uniform pressures behind the pulse. And in fact, one of the issues with interpreting this data is the fact that, well, number one, we have basically non-steady waves going into the material, and you can actually see this in the simulation somewhat here. So at these higher pressures, the wave speeds are a little bit higher than they are at lower pressures at the shock front in this, and so the wave is actually evolving as it goes through the ablator. And in these X-ray experiments, the X-rays, they go through, I should have mentioned this earlier, they go through the entire sample. And so we see diffraction from everything at once. The zirconium, the aluminum, it's all added up at the same time, and we have to be able to try to deconvolve that. So I'm not going to talk about too much of the details. And here I just wanted to talk about the hydrodynamics a little bit. So let's move on here. There are I wanted to talk about some of the features that we can derive from this data. But basically only starting with the aluminum. So we are using the aluminum ablator for both the zirconium, the same aluminum ablator for both the zirconium and the Hopji. And so the conclusions that we came to about the ablator behavior in the zirconium also applied to the Hopji. It was a little bit easier for us to interpret our data in the zirconium case because the diffraction peaks that we have in the aluminum are fairly well separated and are a little bit sharper than the zirconium peaks. So it makes it a little bit easier for us to deconvolve stuff. So basically, we see diffraction after the shock wave has run into the zirconium. So this is a delay after the laser pulse, but it's also after the shock has entered the zirconium. And because, as I said, of the non-uniformity in the compression pulse, we don't see a single line here that is just due to a single uniform pressure throughout the sample. We see this broad distribution, and there really isn't much, I don't think, that we can do about that. I mean, even if we had a pressure pulse that was uniform at the ablation plane, because the timescales are so short, there would be a lot of non-equilibrium phenomena going on at the shock front, including elastic plastic transitions and possibly phase transitions if they're there. And that alone is going to make the response to the material more heterogeneous than it would be in a quasi-equilibrium situation. And then at later times we can see, so this the sharp peak here is the ambient material, and then as the shock wave goes through, it compresses, which shifts at higher density, shifts peaks to the right, and then eventually the shock wave goes entirely through the aluminum, and the ambient peak is completely gone. It's important to note here that at some of our higher intensities, which range above 10 to the 11th watts per centimeter squared, we were a little bit concerned about preheating. So if the intensities are very high, then potentially X-ray generation can occur. And because that can also penetrate the entire sample, you could have preheating, which would change its shock response because the initial material changes a little bit. But to confirm that that's not happening, I'm not showing any pre-shot data here, but we do take shots before with X-ray, or we do take X-ray diffraction patterns before the drive comes in. And if we make comparisons between those and the ambient peak prior to the arrival in the shock wave in the ablator, then by looking at those peak positions, we can estimate what the temperature shift is before the shock wave comes in, and it's not that significant. Okay, and then I think I already said this, at long time scales, the sample is entirely compressed. And at this point, when the sample is entirely compressed, that's when we expect the zirconium or whatever the sample is to begin its compression. And then here is an interesting thing that we did. So at very high energies, we were melting the aluminum ablator. And so what that allows us to do, if we can normalize the ambient aluminum peaks, we can watch them, they can watch them go away as the shock wave propagates through the sample, the amount of ambient material and its associated diffraction peaks go away. And if we have a calibrated estimate of those intensities, then we can estimate how much of the material remains from the shock wave. And so we did that, normalized to the thickness of the material, and you can see that the amount of ambient material kind of goes down as the shock wave propagates through. And then by fitting that to a line, if the shock wave velocity is roughly constant, we can estimate the shock velocity. And then using that estimate of the shock velocity, we can use the Hugonio to get the pressure. And so from this, at our highest ablation intensities, we were able to get a pressure in the aluminum of about 100 GPa. And that was really important for the HOPG, because in the HOPG experiments, unfortunately for these experiments, I forgot to mention it earlier, we were not able to get velocimetry, which is usually a huge problem. And it was a huge problem here too. So one of the great delays in getting this data interpreted was being able to try to infer the pressures just from the X-ray data. The issue is that these are ultra fast, and so you need a very special kind of velocimetry, and we tried to implement that. Unfortunately, things did not work out as well as we had hoped. But if we ever go back to LCLS, I guarantee you we are going to have velocimetry that works. Oh, and I just wanted to quickly show, we also did simulations where we were able to estimate the broad peaks using drives that were kind of comparable. These aren't exactly the same as what we believe in the sample we had in the sample, but we do think that through fairly simple simulations, we can estimate actually what the profile of the X-rays should look like as well. Okay, and then I just wanted to show a couple of our zirconium results before we get to the HOPG. Basically, we did see melting of zirconium, and then longer time scales. We saw that refreeze to beta zirconium. Now, this is not really a comprehensive illustration of all of the data we took. We took data ranging in spacing from, say, 20 to 50 picoseconds out to hundreds of picoseconds at very long times. But as I might have mentioned earlier, we took more than 700 shots, and most of that data was at different delays. So we did look at different pressures as well, but we got a ton of different delays, and the delays that I'm showing here are really just supposed to be representative of sort of where we saw transitions between how the material was behaving. At lower pressures, we certainly did see at equilibrium beta zirconium showing up if we were at pressures that were in that part of the phase diagram. But then there was also a part of the phase diagram at lower pressure around 13 GPa along the Hugonio, where we are in the omega part of the phase diagram. And we believe in that part of the phase diagram, we saw BCC. And the reason that's important is BCC is not the equilibrium phase. So what we believe we saw was probably an intermediate phase to the final BCC phase, and that is that has some support in the literature. But there was a lot of debate about whether or not that was what we were actually seeing, and I would argue that that probably is still an open question to some extent. I'd really be interested in seeing other people look into that and see what they get. Okay, so let's talk about HOPG a little bit. So HOPG is highly oriented pyrolytic graphite, layers of, everybody knows this, but layers of graphene sheets that are very strongly sp2 bonded in the plane, but not so strongly bonded out of plane. And the phase transition from these initial graphite sheets into diamond involves intra-layer bonding as well as shear between the bonds. And I will talk a little bit about more about that in a moment. And that is a complex process. One of the nice things about using shocks to explore that is some of these mechanisms like shear and diffusion, thermal diffusion, happen on long enough time scales that you can imagine they might be limited by this time scale of the compression. So if we compress very, very rapidly, it may be that macroscopic scale shear doesn't have time to occur. And that is speculated, or at least something like that. I can't say for sure, but something like that is speculated to be the reason why in impact events, this has been known since the 60s, in impact events, the transition from graphite to diamond forms a non-equilibrium phase, the Lonsdaleite phase. And I'm not going to get into some very long debates about what that involves. I'm certainly no expert in that. Nonetheless, there is debate within the community over whether or not Londsdaleite actually exists as an equilibrium phase. It's not on the phase diagram. And so some people think that it's just a very disordered form of regular diamond. But I'll talk about that right now, as a matter of fact. Okay, so to kind of begin to understand this or get some perspective on it, I wanted to introduce some shorthand for thinking about how these graphene layers are arranged with respect to each other, and just kind of a historical note. This picture, I don't know if this picture was originally devised by Evan Reed. People have been thinking about this for a long time, but Evan was the one who told me about it. And I've got a little picture there of the cocktail napkin that he explained this to me at a conference in 2018. And so I wanted to put that up there because just to note that if we're looking for ways to fondly remember Evan Reed, this is one of many of them. Okay, so what's going on here? Well, we have a unit cell here of graphene in 2 dimensions, and then we have the actual graphene itself, and there are basically 3 different places where the graphene can be oriented with respect to the unit cell. The first is the A stacking, B stacking, and you'll notice sort of what I'm kind of keeping constant in this is this apex here in the middle. And so if we move the unit cell with respect to that, it can be in 3 different positions, A, B, and C, with respect to that apex, and that defines stacking in graphite. And then we can talk about some rules that we might apply to how those layers, those graphite layers, might bond to each other. And typically they will only bond A to A, B to B, and C to C, and only one out of plane bond. And that's really important to realize because that is something that limits how these phase transitions can occur. And so when I say that the allowed out of plane bonds look like this is ABC stacking. And so this is the kind of stacking that is typically found in cubic diamond. This is the final state that we would like to get to. And so this is sort of the morphological or the schematic way in which cubic diamond is structured compared to what it would have come from graphite had it come from there. Now, there are probably people in this audience who know a lot more about the details of these structures than I do, and I hope not to get into a huge debate about that very specifically. I just wanted to present sort of a 0th order approximation to how Evan thought about it and how I think about it. But I'm sure there are a lot more details, particularly when we're thinking about this, including defects on macroscopic scales. Okay, so here is where this single bond per intralayer rule comes into effect. Effectively, what this means is that if we were trying to do bonding without any shear, we wouldn't be able to do anything more than create bilayers. And the reason is because those bees can't connect. So the set of bees on the left here can't connect to the set of the bees on the right. And the reason is because they've already got a bee that they're connected to, and we can only have one bond. And so if we were to make the full transition to cubic diamond, then it involves multiple steps, as hypothesized by Mundy in a paper in 2008. So this is for a very, very fast shock. They did MD simulations of. And the process by which they hypothesized this might occur is they first form these 2 bilayers, which cannot connect. This is not an equilibrium state, right? So if you were to take the pressure off, these bilayers would go away. And in fact, one of the goals of our research originally was to see if we could detect those bilayers. I don't know if we did or not, but it is an interesting open question. And then after the bilayers form, some shear has to occur. So we have to shift these letters over a little bit so that now we have two C's next to each other that are not currently bound and can bind to each other. And at that point, we have cubic diamond. And that is ideally the way the process would go under very fast shock compression. Is that what actually happens? I have no idea. It's a hypothesis. And then, so I just wanted to provide some perspective on how defects might be related to hex layers and why thinking about hex layers or Londsdaleite diamond can be a little bit thorny. And the reason is because, well, it's not so clear how hex would form using this kind of picture unless you have, number one, something like defects. But then even then, how do you make extended hex? So this is still kind of an open question. You can imagine if you did have a stacking fault. So let's suppose we have a stacking fault in our material, then you could shear things in a way that you get the ABA stacking that's associated with hex. Sorry, I probably should have said that earlier. Cubic is ABC stacking, but hex is thought to be AB stacking. But even in this case, you don't have like an extended material. So I would say this is an open question, but it has helped me anyway to think about it a little bit. Okay, so let's talk about the experiment. See how much time we have here. The experiment, as I say, is completely analogous to the zirconium experiment, but instead of using zirconium as the sample, we are using Hopchi as the sample. In the Hopchi experiment, well, I mean, it's not exactly the same. We assumed we could get reflectivity off of the back of the zirconium for our would-be velocimetry when we did the experiment. But in Hopchi, we covered the back of the Hopchi with an aluminum layer, and nominally that was for our would-be velocimetry. But the nice thing about that is it did give us a calibration for the ambient aluminum position, even after the aluminum on the ablator side had been completely ablated or completely changed. Generally, we can, even in the Hopchi case, we can estimate pressures from peak shifts. But one of the problems in dealing with a Hopchi versus aluminum is that the spectra, the diffraction patterns are quite congested with Hopchi and other kinds of lines, or Hopchi and diamond lines that may overlap some of the aluminum lines, which makes it a little bit difficult to see where shifted peaks might be. So we, it's not so trivial to deconvolve those, which is one of the reasons why it was very nice that we had calibration data from the zirconium experiments at the same conditions that we had for the Hopchi. So let's talk a little bit about the equation of state. So I've got, the phase diagram and an equation of state here. This equation of state is from laser-driven experiments by Dominic Krauss from 2016. And then we had our own model that Ryan Austin developed to fit these to do hydrodynamic simulations. And you can kind of see also from these where we expect to see the different kinds of material states. One interesting thing to note about this is that these green peaks are diamond, cubic diamond, but Krauss didn't see Londsdaleite until they got to pressures that were substantially higher than that. In our case, the maximum pressure that we saw in the aluminum ablator was about 100 GPa. And under those conditions, using the equilibrium Hopchi or equilibrium graphite hugonio, we would only expect to see a pressure of about 80 GPa. And that is at a pressure where Krauss saw some kind of diamond, but only cubic. In our case, though, we're claiming to have seen Londsdaleite. And I don't have an unambiguous explanation for that other than to say that perhaps the time scale of our experiment played a role, and perhaps the phase transition to the equilibrium state was a little bit further along in Krauss's experiments than it was in ours. Let's see, was there anything else that I wanted to say about this? I don't think so. Oh yeah, there was one other thing, sorry. Yeah, the other thing I wanted to say about this was that, these equilibrium estimates of pressure may not be entirely accurate. And the reason is because, of course, the Hopg is not in an equilibrium state. It's probably highly non-equilibrium, closer to elastic compression, much as the aluminum was elastically compressed in data that I showed you earlier. But that wouldn't mean the pressure is lower, or certainly wouldn't mean the longitudinal stress is lower. If we were in a situation where we were compressing, a more elastic-like state, that equation of state would be, or whatever you want to call it, that stress-strain response would be above the Hugoniot. So the pressure, the nominal pressure stress, whatever you want to call it, would be above what it would be at equilibrium. Okay, so here are some simulations that we did. These simulations were not so much to tell us what the pressures were. We believe we know what the pressures were from our characterization of the ablator. What these were mainly to do was to tell us what the timing was, mostly the timing of the arrival of the compression wave at the Hopg, so that we could corroborate changes in the Hopg that we saw in the diffraction patterns with when we would have expected to see those changes based on the propagation of the shock front. And these are just the sort of two limiting cases. It also gives us some idea of what the material state is. So here's a cut of the material at 280 picoseconds, and we can see how much compressed material is of the Hopg versus the aluminum for these two different pressures. So again, we claim that we're getting a pressure of about 80 GPa in the Hopg, but the stress, if that's what it is, could be higher than that. So this is, I'm not going to try to interpret this. This is not to illustrate, any particular phenomenology, besides to say that we spent an awful lot of time looking at these waterfall plots and this does give a better idea of how many shots we took. This is for a single energy. And different spacings for the timing, and you can see peaks popping up here and then moving around, depending on when the sample compressed and decompressed. But we spent an awful lot of time trying to think about data in this form, and without really getting anywhere. And essentially, what we concluded was that the problem was we were integrating over the entire azimuthal range. And by integrating over the entire azimuthal range, we were effectively swapping out signal that was really the more relevant signal in a limited azimuthal range. So I'll show you a bit of that in a moment. So I don't want to repeat myself too much. I put a slide in here that says something very similar. These data are significantly, data for the Hopg are significantly different than what we get in polycrystalline diffraction patterns. And so if you're looking at a polycrystalline diffraction pattern, you effectively see if everything's at equilibrium, you effectively see a ring, and then you integrate the azimuth around that ring and you get a nice peak. Well, we can't do that here because we are very far from equilibrium, and we are certainly not seeing rings over the entire azimuth. So this is also just to illustrate that Oliver Schauner at UNLV was the one who really broke the code on this one. So he had done a lot of fits, and he did a lot of work with different azimuthal ranges. Again, I'm not so much going to talk about this, just I wanted to present sort of a work in progress, a work in progress figure that he sent to us when we were beginning to think about this. And he did a bunch of fitting at using different techniques. Again, I'm not an expert in that, but at the end of the day, his conclusion, and this was the first time we had heard someone say this, his conclusion was that we actually were seeing hex time based on these fits. So I wanted to show this a little bit more closely, the way in which our data differs. I'm not going to show a ton of data. We have a ton of data, and I don't want to go through a laundry list of our data. I just want to try to point out the most sort of incisive data sets that we got. So basically we have pre-shots, and so this is a characterization of the sample prior to the drive ever coming in. And then the in situ shot. And what we're doing here is looking at three different azimuthal ranges. One is up here, that corresponds to down here. The other is here, that corresponds to the middle here. and then one is out here at larger Qs over here. And the first thing to point out is, and then we have dashed lines out here that show let's see, what does the dash show? It shows the pre-shot. And then the solid lines show the in situ. And if we integrate over these limited azimuthal ranges, then we can clearly see the appearance of spots at positions that are consistent with Londsdaleite. And the reason why this is interesting, and I think groundbreaking, is because this is not something that people typically observe. We are clearly far from equilibrium. We're not just talking about texture here. I mean, these may be single crystal spots, and we don't have that many of them. So what that indicates is that these samples are very highly textured, very highly oriented, and that the product is very likely strongly oriented with respect to the initial state. And this implicitly confirms a speculation by Nellis years ago when they did their shots on graphite, that this is a martensitic transformation. This does seem very consistent with a diffusionless transformation. Okay, believe it or not, I am almost done. I mainly just wanted to cover the kind of essentials. So from the perspective of a simple way to understand this, I like these kinds of plots where we consider the two different structures that the sample might be. We take the lines that we would associate with that structure, and then we plot the density that we would infer from those three different lines. If they all overlap, then that would seem to support an assignment of the structure that we're hypothesizing. And if they don't overlap, that would seem to support that it's not that structure, it's something else. So I have two on-site structures here. One is the Lonsdaleite on the left, the other is graphite. One thing that is important to note about these experiments, we may well be seeing an intermediate here. And the reason is because while the sample is under compression, we believe we're seeing Londsdaleite, but once that pressure is released, it seems to transform back to graphite. And this could also potentially be consistent with the original hypothesis of Mundy, that they may be seeing this layered bilayer diamond form, which is not an equilibrium form, and we would not expect that to form a diamond as well. The other piece of corroborating evidence we have here is that this density for Londsdaleite is along the Hugonio at a pressure of about 80 GPa, and so we feel like everything is pretty consistent. Okay, so what we feel like we know for sure is that we have high pressure in aluminum, certainly on the order of 80 GPa or more. So I say here that we're less certain about the pressure in the graphite because of the non-equilibrium issues we talked about. But as I said, whatever the stress is, stress or pressure, it will be higher than the Hugonio, assuming that the aluminum is at 80 GPa. The new lines certainly appear, and they appear at a time scale that is consistent with the shock wave arrival at the Hopschi. And I'd like to note, I didn't say this, I should have said this earlier, that those lines form very rapidly within tens of picoseconds of the shock arrival in the Hopschi. And so whatever's going on, it is very fast. And it is very highly structured. And we believe that Londsdaleite best explains this data. Okay, so that was a long adventure over the last 6 years. We are looking for postdocs. So if there is anyone who is interested in doing wonderful work in the service of national security, that also might include very exciting science, then I invite you to contact me. We have a number of postdoc positions available, and I would love to hear from you. Thanks. I'll take questions.
Thank you very much, Mike. Very nice work. So the talk is open for comments, questions. Feel free to unmute yourself or use the chat. Maybe I'll start off with a question. Coming back to the point you made at the outset about the so-called controversy between Lonsdaleite and just disordered cubic diamond. I mean, how can you rule out that you don't have simply diamond that has a lot of stacking faults that gives you the peaks, in the right place that you would expect when you have stacking faults that happen to match Lonsdaleite?
I don't think we can rule that out. I think that we have an interesting new state. I think we've observed an interesting new state. I think we can assign it to Londsdaleite, whatever that is. But I don't think that we have perspective on what it is. I do think that that's an interesting question to explore.
And likewise, you referred to the 2016 study of graphite and diamond and Lonsdaleite. Did they see a well-defined transition or well-defined difference in the graphite versus in the Lonsdaleite versus the cubic diamond? Did they have, or was it just a gradation in disorder that ultimately starts to look like Lonsdaleite at one end and cubic diamond at the other?
I wouldn't say that I could answer authoritatively about Krauss's work. So I will leave it at that. So I would suggest that you contact Krauss and talk about that in more detail. And part of the reason I hesitate to comment is because just having gone through this, particularly debates about whether it's Lonsdaleite or cubic or graphite for the last few years, this is very controversial, and I don't want to stir the pot. I'm not an expert in carbon or disorder. So,
okay, thanks. Comments, questions?
Mike, this is Steve Gramsch. Could you say a little bit more about your choice of how you carried out this experiment, the conditions that you used? I mean, would a faster or more high-powered laser facility or technique not allow you to see the things that you did, or would it maybe help?
Well, we're very limited by the laser, unfortunately, because there are very few lasers out there that have the combination of an extremely fast rise time and a long duration that will give a constant pressure at the ablation point. So if someone were to engineer a laser out there that has a 10 picosecond rise time, maybe sub 10 picosecond rise time, then rises to a constant intensity and holds that for 10 nanoseconds, wow, that would be fantastic. There are lots of other things too that you can imagine doing. You could imagine putting a thin graphite layer between two impedance match materials, and then looking at peaks come and go depending on the pressure that I mean, I don't know if I'm answering your question or not, but I definitely would say that we're limited by the laser. And if laser technology got to the point where we could do a fast rise with a constant intensity hold, then that would be fantastic. But note that if the longer you make the experiment, the more energy you need. So, so if you were to try to go out to longer time scales like 10 nanoseconds, which is maybe what you need to get to cubic, then yeah, you definitely need a really high energy laser to do that.
Thank you.
Okay, Hussam has a related question. Do you want to ask it?
Hi, thank you for the talk. By the way, it was quite interesting. I was just wondering if you went up to 80 GPA for the HOP-G, and I was just wondering, was that your target in mind? Would we see similar trends if we go beyond 80 GPA? Just kind of like the process behind that. I was just kind of wondering what was going on.
Our target was basically 100 GPA in the aluminum. And the reason it was because we wanted to get into a regime where other people had, we wanted to get to a pressure above about where people had seen transformation of diamond in the past. So in shock experiments, most people know that where you see this transformation occur depends very strongly on how fast you compress. And if you're compressing on diamond anvil cell timescales, and perhaps like even in an RDAC, and you can put in some shear yourself, I mean, the pressure might go to something very, very low, right? Whereas if you're hitting it with a shock, you really do need to hit it hard to see the transformation occur. on like nanosecond time scale. And we just wanted to make sure that we were in that regime. These kinds of experiments are challenging because we don't have very specific quantitative questions. We have more, I would say, phenomenological questions. So we want to get into the regime where we're seeing phenomenological things, but we're not trying to measure an equation of state to 1%. We can't do that, right? What we hope to do is be able to see broad distinctions that tell us, general information about the phenomenology that's involved in the phase transition. So maybe I over-answered your question, but did I at least answer your question?
Oh yeah, no, you answered and you also provided insight, which I appreciate.
Okay, thanks. Can you say a little bit more about the experiment you showed and mentioned that you had a lot of shots? So how many samples did you have to prepare, and how many did you look at, and how difficult was the sample preparation?
We did not. I think we prepared something. I don't remember exactly, but I think we prepared something like 10. And I think when I went into that experiment, I wanted to get thousands and thousands of shots, right? And had we, what effectively happened was we ended up trying to set up the velocimetry for much longer than I expected that we would. And so we only got shots for like that 700 shots. That was like in one evening. What I had expected was that we were going to have a week of shots, and we were going to get many, many thousands of shots at many energies and many time delays. And so, but to do that, there were 225 wells on one of those silicon wafers. And so to get, if we have 10 of them, then we have a couple of thousand sample positions. And so that is the order. I don't remember exactly how many we made, but we made about that many for both the Hachi and for the zirconia. And
so within a given sample, you have 1,000 positions you can look at, or
about 200.
200. Okay. Okay.
Peter.
Hey, Mike. Yes, great talk. Thanks for the really exciting results, and I'm looking forward to looking at your paper. Congratulations on that getting published. And I had a quick question regarding the samples that you take back from the X-ray diffraction experiment. I was curious about the size of the region that is being converted to potentially Londsdaleite or other phases of carbon, and whether you may have.
Go ahead.
I was just curious if you may have looked at these samples with optical spectroscopy in terms of the point effects that might be formed in the sample if you have hexagonal diamond or hexagonal phases. I'm curious if there might be signatures in just standard photoluminescence measurements or maybe Raman in the samples. But I don't know if the cross-sectional size of the samples is enough to probe with a visible wavelength.
Well, over these time scales, and so you might have noticed that the graphite in this this only lasted for tens of picoseconds, and so if you were to use, I don't know, it might be possible to use something like use some coherent technique, coherent Raman technique, but usually the limitation, as if you're using spontaneous, is you just don't get any photons out, right? So if you were to use like maybe some sort of three-wave mixing, multi-wave, four-wave mixing, something, you might be able to get enough out. But I do feel like I also didn't answer the original question, which was so we have a spot size that is kind of tens of microns across, 50-ish microns across, and then the samples, a few microns thick. So that's not a huge volume, but one of the things that we thought about doing in the past is using some kind of catcher, so aerogel, for instance, to avoid reshocking, and then taking a sample and then just rastering and taking just many shots and catching the ejecta that comes out the back, and then using a technique like an optical technique or SEM or something, right? Some TEM to look at more closely at what comes out. And I think that could potentially really be exciting for the sake of comparing to like actual impact data. The question of what the defect situation is really an open question. And I would love to do comparisons of like in situ, like post-mortem, whatever the product is. I'd like to make comparisons to actual real samples, longer duration experiments. Did I answer your question?
Yeah, that's great. I was excited to see your data because in some of the shock literature I've read, sometimes there are small grains of diamond left over that might have some detectable optical signatures. But I wasn't sure if you had diamond left over in your recovered material.
No,
I'd love to chat offline.
So Peter, let's totally talk about it, but we'd have to do a new experiment, because what happens in this experiment is the stuff that gets blown out of the back of the sample into a giant vacuum chamber. It's gone forever. So.
Got it. Thanks, Mike. Beautiful results.
More questions, comments?
Yeah, so I have a quick question here. So first off, thank you so much. It's very interesting to see some of these techniques that you used. On the illustration where you showed the different layers, where you had your, I think it was the silicon nitride, then aluminum, and HOPG. Was that another aluminum layer at the back? And what is the point in that?
The point of the aluminum layer on the back is to provide reflectivity for velocimetry. And but the nice thing about this, and I think it would be an interesting thing to think about for other experiments too, is it also does provide you with a calibrant, right? So you have cold aluminum on the back, and it will also tell you about an arrival time of the shock when it gets to the back. But originally it was there just to provide reflectivity for velocimetry.
Oh, okay.
You're talking about this layer here.
Yep. Yeah. Great. Thank you.
Thanks, Zach. Okay. More questions? If not, Mike, we're at the top of the hour. Thank you for a great talk, and thank you all for joining us. I'll see you next time.
Thanks, everybody.